Thank you, and thanks for staying. Can you hear me okay? Okay. Yes, Mark says yes? Okay. So I'm going to tell you a little bit about our research. My lab is over in the medical school. My office is here in the Nano Institute. And if you had to design a nanotherapeutic vehicle, something to carry drugs, you might want to design something that Hollywood thought of. And this movie, Fantastic Voyage, which is a lot older than all of you, designed this little submarine called the Proteus to carry scientists that they shrunk down in size. And the Proteus had a lot of problems. It got attacked by the immune system because it was foreign, so it didn't work very well. So people thought about it. If you had to design a delivery vehicle, it'd have to be very small in size. It has to get through the filters in your body and the kidneys and other places. You'd want to have a large payload inside. It'd have to protect the drugs. It'd have to be safe. That was the problem with the Proteus. It wasn't safe. It would be nice if it had a GPS system, if you could target it and control the release. So people have been working on this problem for a long time, and they've been considering viruses have a lot of the right attributes to be drug delivery vehicles. They're really a good size. They have a good payload size in the inside of them. They're very stable. But the problem with viruses is that the human immune system has been evolving for millions of years in order to try to stop viruses from getting to us. So there are some problems with compatibility. And so instead of viruses, we've been studying a particle that's a natural human particle found in every cell of the human body, and it's called a Volt particle. And this is an electron micrograph of the Volt particle. It's an oblong-shaped particle, about the same size as a virus. But instead of a virus, it's a completely human particle. It's completely compatible with the immune system and human. And we first found, a postdoc in my lab, Nancy Kadersha, and I first described the Volt particle back in 1986. And because they were composed of these multiple arches that appeared to make up their surface, it reminded us of the vaulted ceiling of a cathedral, and that's where the name Volts came from. A lot of my colleagues thought we should have named them raspberries or hand grenades or hot dogs. I don't think they look like hot dogs. Well, maybe a little bit. So if you want to know how big a vault is, I blew up a human white blood cell here and projected on the screen. This is magnified about 2.5 million times, and a Volt particle would be about the size of this yellow dot right here. We made an antibody against the Volt particle, and we made the antibody fluorescent so we could stain vaults in human cells. And this is a human fibroblast stained with a yellow antibody against vaults, and you can see that there are literally 10,000 vaults in every cell of the human body. So it's a natural nanoparticle. So we learned how to make vaults by taking an insect virus and putting the DNA that encodes the major protein of the Volt particle into the insect virus and infecting insect cells in culture. We expected to get this protein, the major Volt protein, made, but we didn't see any of the major Volt protein. Instead, we saw vaults. So vaults are made by the cells, and they assemble into Volt particles in the insect cell. But the difference is that these Volt particles are empty. And this is a crystal structure of the Volt particle. This is a single major Volt protein shown in its crystal structure, and 78 of those proteins come together to form the Volt particle. And you can see it's a shell with all these proteins around the outside. They're all the same protein, but 78 copies of this major Volt protein make up the shell of the Volt particle. So we had to figure out how to package the vaults with different components. And it turns out that the Volt shell in normal vaults in your body and my body contain these other components, including this enzyme called VPARP. And Valerie Kickhofer in my lab figured out that VPARP had a signal on the VPARP protein that was responsible for binding it to the inside of the Volt particle. The Volt particles that we make in the lab are hollow. They only have the major Volt protein. They make up the shell, and none of these other components are inside. So we borrowed that zip code from the protein VPARP, and we attached it to an enzyme, luciferase. It's the enzyme that gives the firefly its glow. And we did that so we could follow this around in the test tube. So we transferred the zip code to luciferase. We expressed those vaults in the insect cells, and we looked on the inside, and we found this luciferase protein was packaged into 2 rings of density on the inside of the vault particle. So we figured out how we could get proteins like luciferase to go into the vault particle. And that's kind of our strategy for putting drugs and other proteins into the particle. Remember how Dr. Dr. Maynard showed you how proteins drugs are a lot of proteins. So we were thinking about packaging protein drugs into the vault particle using this strategy. And so we started collaborating with a group of oncologists at UCLA, particularly Dr. Stephen Dubinet, and he's a pulmonary oncologist, a lung cancer doctor, and he's very interested in fighting off lung tumors. And the problem with lung tumors and other solid tumors is that these tumors create an environment that prevents your immune system from recognizing the tumor as foreign. And right now, the biggest strategy in cancer therapy is to try to overcome these barriers that keep the immune system out of the tumor. And you might even see on TV now, there's a bunch of new drugs that are advertised on television. Keytruda, for example, is one of them. And these are drugs to try to break down the barrier to keep the immune system from fighting off the tumor. So what drug are we going to use? Well, Steve had been studying a drug called a chemokine. And this chemokine, called CCL21, usually lives in the lymph nodes. And as you know, when you get an infection, it usually drains into your lymph nodes. The lymph nodes turn out to make a chemical gradient of CCL21, which attracts the immune cells. These are called T cells, and these are called antigen-presenting cells or dendritic cells. It attracts them into the lymph node where they can fight off, where they can make an antibody response or an immune response against the antigen that's in the lymph node. And so Steve had developed a therapy whereby he engineered a cell to make CCL21, and he could inject that cell into the tumor, and the CCL21 would attract the immune cells into the tumor to try to get an immune response against tumor antigens. And this allows the immune system to see all the tumor proteins, which are called tumor antigens. It enhances the potential for an immune response against the tumor, and you could even imagine that you could treat other solid tumors by this same methodology. And so Steve did this in an animal model where he injected these cells that contained the CCL21 into the tumor, and after a short period of time, the tumors were destroyed in the mice. And he even took it to a human clinical trial here at UCLA, where you can see on October 13th, a couple of years ago, when this very large tumor in the lung was injected with the cells, about 40 days later, there was this massive amount of shrinkage of the tumor. But the problem with this therapy is it's very expensive. It's a cell-based therapy. He had to engineer the cells of each and every patient in order to treat them with their own cells. And so it's not very practical for drug therapy. And so we asked the question, could we use vaults as an off-the-shelf reagent to deliver the CCL21? The idea would be that we would engineer a vault particle containing this drug, that it would release the CCL21 and attract the immune system into the tumor. And this would be what you would call a real drug, one that you could make, use it for every patient. You wouldn't have to do personalized therapy. It would be what you call an off-the-shelf reagent. It would be consistent, have dose control. It would reduce the cost. So we manufactured a vault particle containing that CCL21 protein that we attached the zip code to allow it to package into the vaults. And you can see the vaults that we made have these little white bands in them because they're packed full of this CCL21 protein. So it worked very nicely, and we could make the vault reagent. We could inject the empty vault into an animal tumor, and the empty vault did nothing. The tumors grew very quickly in size. But if we use the CCL21 containing vault, we could dramatically slow the growth of the tumors precisely the way the cell-based therapy worked in Dr. Dubinet's hands. When you look at the tumor itself, vaults, the empty vaults, nothing happens to the tumor tissue, but in the CCL21 vaults, we get a massive infiltration of immune cells. These little bright green cells here are the immune system coming in to attack the tumor. So in fact, we are reproducing the work that Dr. Dubinet did with cell-based therapy now with a vault particle therapy. And we're a little bit early. We haven't yet gotten into humans yet, so I can't say that we have drugs designed yet, but we think that we'll be in a human clinical trial with our vaults by next year. And that's thanks to a company that we started called Vault Pharma, which I'm involved in. And Vault Pharma is now trying to take this therapy into humans in a clinical trial. So we have a lot of different laboratories that we have collaborated with here at UCLA or are collaborating with, and collaborators around the world as well. And happy to end now so we can get the next seminar going. I can answer a question while Dean's setting up. Any questions? You're welcome.